All right, so yesterday we dove into a lot of trigonometry, maybe waking up some very pleasant memories or maybe some with not so pleasant memories. But either way, as a reminder, you have this chart in your notes that has all of the derivatives for the 6 trigonometric functions. So we have sine, cosine, tangent, and we have cosecant, secant, and cotangent. And the color coding here was just us trying to think about some strategies to help us remember the different ones. And one more layer I want to add on here right now is that the sine, cosine, tangent, these 3 trig functions are known as the 3 main trig functions. So typically when someone says trig functions, they're saying sine, cosine, or tangent. But the cosecant, secant, and cotangent, those are known as the 3 reciprocal trig functions. And so if you're looking to Google some resources or you simply want to read up more on the 6 trig functions, the main trig functions and the reciprocal trig functions might give you a little bit more direction in terms of what you're Googling. All right, so we've got these 6 derivatives. They're going to come up fairly frequently, but I think that the sine and cosine ones come up the most. I think the tangent and cotangent come in sort of second most frequently. And then the cosecant and the secant are a little bit less frequent than the others, okay? All right, so let's hop back in. Let's do example 6 and 7. That's the last pieces of the trig lesson. And then we will move on to a very important rule called the chain rule. Okay. So example 6 says find d to the 4th y dx to the 4th of sine x. And one of the things that is really important to know when we're reading math is like, what are these symbols telling us? And so I believe in a different question, you've seen dy dx. We've seen that a lot. And we know that means find the first derivative. But we've also seen this notation. And this, I just want to point out, is the same as saying y double prime, or like find the second derivative. Okay, so if we leave a little bit more space in here, maybe we can write in a reminder that dy dx is the same as y prime. D squared y dx squared is the same as y double prime. And we can sort of keep going. If I have the third derivative, I might write it something like this, or y triple prime. And then after 3, we tend to start to use numbers. And so this one, the 4th y dx to the 4th, is the same as y. And this gets tricky because we're looking at these primes are actually like Roman numerals. So we have 1, 2, 3, and then if to write 4, it's like IV. Okay. Because we sort of run out of Roman numerals, well, we don't run out of them, but I think we just don't know those quite as well. Sometimes this notation is a little bit easier to interpret. Okay, but in essence, example 6 is just asking us to find the 4th derivative of sine. Okay, so this notation right here is saying find the 4th derivative right? So let's see what we have. Our initial function is sine x. What is y prime? Yeah, there we go, cosine x. All right, now let's find our second derivative. What's the derivative of cosine? Good, negative sine. All right, so we've got our first derivative, second derivative, so we've got 2 more to go. All right, what's the third derivative? Or in other words, what's the derivative of negative sine? Yeah, this is going to be negative cosine x. All right, then it might be helpful for us to think about this as like a -1 times sine, and then we can use our constant multiple rule. Okay, so we're almost there. We've got 1 more to go. Y, the fourth derivative, what do we have? Ooh, nice, nice. Yeah, we end up, well, shoot, we end up where we started. We started with sine x, we took 4 derivatives, and it turns out that the fourth derivative is actually the same as our original. Okay. So something like this is pretty good practice in terms of thinking about the positive and negative versions of what they're going to be, okay? Because at some point we have start to throw negative sign in there and we have to figure out how to compensate for that. Yeah, it's kind of like the power of a negative where things sort of alternate. But for those of us who maybe remember, how many of us remember learning about the number I? Anybody remember the number I? Yeah, okay. So fun little non-calculus exercise. If we have I, we know that's the square root of -1. What if I do I squared? What do I get? Yeah, I get -1. Okay. What about I cubed? Not quite, not quite. I cubed, we could maybe write as like I times I squared, which is going to be -I. Yeah, because I have a -1 times I, that gives me -I, okay? And what about I to the 4th? There we go, I to the 4th is 1. And so when we think about the next one up, I to the 5th, that's going to get me back to I. All right, so even though they're very different functions, right? We have sine and then we have imaginary numbers. This idea of like a cycle of 4 where you sort of start at one place and then you get back to the same place. Hang on. Sorry, my screen was frozen. Okay, there we go. Sorry. So this idea of a cycle of 4 things and you end up where you started, we actually see that also with the imaginary numbers if we're just looking at I. Okay, so the thing in purple is just a little nerdy side bit in case you were curious about like, where else in math do we end up with a cycle of 4 and we end up where we started, and I is another place where that happens, okay? All right, we've got one last question here. And this time we're just going to be finding the first derivative, but we get a chance to practice a bunch of different rules and some of our most commonly, I don't want to say that they're common mistakes, but kinds of exponents that folks tend to find a little bit challenging. And so I really want to take some time to dive into that. So example 7 says find the first derivative if f of x equals 3 over x to the 4th minus 2 square root of x tangent x, right? So you can see here we've got a problem that has some negative exponents, some fractional exponents, some trig, right? So we're sort of mixing together a lot of the different strategies we've learned. And in particular, we should begin the same way where we take a moment to rewrite our function in a way that's going to be beneficial for us, okay? So how might we rewrite f of x so that we know it'll be easier for us to take a derivative? All right, I see a 3x to the negative 1/4, and I'm going to say almost, not quite. Okay, so we're going to do 3x to the negative 4, okay? So 3x to the negative 4. And so because this x to the 4th is on the bottom, we just want to make that exponent negative, not into a fraction, okay? And then for the second term, we have negative 2x to the 1/2 tangent x, all right? So let me pause here for a moment. Are there any questions about how we rewrote our original function? All right. So we have not done any calculus yet. All we've done is rewrite it. So now let's find first derivative. All right, let's find the first derivative. I'm actually going to leave a little bit of space here, just because personally I like to jot down for myself what rules I'm going to be using before I get started, because sometimes when I start a problem, I might forget some of those rules because I get caught up in the problem. But if I identify them first, it makes it a little bit easier to know these are the rules I'm going to do, okay? We can use difference rule, quotient rule, and product rule. Do you mean use the quotient rule for 3 over x to the 4th? Yes, you can, okay? I think typically for something like this, it's quicker actually to use the power rule if we change it. Just because with quotient rule, we have to do like the u and the v, the du, the dv, and then plug it all in, okay? Yeah, but it is possible, it is absolutely possible, yeah. All right, so what rule would we use for our rewritten first term over here?
Power rule?
Yeah, we're going to use power rule. We might want to make a note to ourselves that we're also doing a constant multiple, right? Because I have a 3 times x to the negative 4. And that I think is just a reminder based off of some of the questions from yesterday, like does the 3 go away to 0 or not? But I think if we remember it in the context of a constant multiple, we'll know it doesn't go away. But what about this second term right here, the 2x to the 1/2 times tangent x? What are our thoughts on that? Yeah, we're going to use product rule as the bigger structure here. We want to maybe think also we're going to need power rule for that x to the 1/2. Yep. And then while we're here, we might want to even remind ourselves we have a constant multiple because we can leave the 2 out in the front while we do the product rule, okay? All right, so let's do some setup. Let's do this one over here. So we'll say u equals x to the 1/2. V equals tangent x, okay? We're going to use power rule for du. We'll get 1/2 x to the negative 1/2, but we know we can write that as 1/2 root x. And dv, we learned yesterday, we've got tangent x. Let's see, that derivative should be positive because tangent doesn't start with the letter c. And that's the secant squared x as that derivative. There you go. Good. All right. So I think that's sufficient for a setup. We can now probably go ahead and find our derivative of the first term and then use what we found to plug it in for the derivative of the second term. So power rule says we're going to keep that constant in the front. We're going to bring down that negative 4 x to the negative. What's the power going to be here? New power for x to the negative 4. Good, because x to the negative 4 minus 1 gives us negative 5. Good, good. So that first term we've taken care of. Minus 2 times, we're going to plug in things into our product rule. U dv plus v du. And we'll get x to the 1/2 secant squared x plus 1/2 root x tangent x. All right, so we've plugged things into the power rule. I know yesterday I said I like to write out the power rule first. So we've got our u dv plus v, whoops, v du. All right, so you've done the calculus at this point. If you've shown me all of this setup and you've got all of this correct, you're literally 9.5 out of 10 there. Okay, so let's make sure that we finish things off by simplifying appropriately. And we'll end up with negative 12 x to the negative 5 minus 2 square root of x secant squared x minus tangent x over square root of x. Now I did quite a few steps in here, so let me pause for a moment and see if there are any questions about where this number went or where this number came from or where the sign came from. And then we'll do one last cleanup before we box off our answer. Yeah, that's the last thing we're going to do. We're going to turn that first term into negative 12 over x to the 5th. Okay, so I'll start to write that. Okay, the interweb seems to be a little fussy today. Hold on. This is always super fun. Oh, come on. Okay, there we go. Okay, there we go. My apologies. All right, so the last thing I do want to write for this is let's just convert that first term into negative 12 over x to the 5th, and then everything else will stay the same. All right. So let me bring this all into, whoops, one page. You can take a look at that. And because I know we just had a little bit of a pause in the screen sharing, let's see if there are any questions that we have here.
Professor, I have a quick question.
Absolutely. What's up?
Where it goes right before the simplify. So actually in the simplify you have the minus 2 square root x secant squared x minus tan square root x. How did you get that second half of the equation?
The tangent x over square root of x part?
Yes.
Okay, like this term.
Yeah.
So where that came from is, if we go back in a little bit, I have a -2 here. And I was going to take this -2 and I'm going to distribute that to both terms, right? So the -2 is where I get this -2. But look at what I have. I have -2 times 1/2. So that's going to give you -1. So if I write that out, -2 times 1 over 2 root x tangent x, then I think we can see this 2 and that 2 reduce. And so we'll end up just with the negative tangent x over square root of x.
Okay, that makes sense. Thank you.
You're welcome. Abby, yeah, so I think that UDV or U prime V plus UV prime is going to end up being the same thing for the reason that Matt said. And what folks typically do is it is about plugging things into the formula. But remember how yesterday I said like the trig stuff tends to come at the end. So in this part right here, I was doing VDU, but because my V is a trig function, I actually just wrote it at the end. Because I know that like typically we write the trig function at the end. So I moved it to the end. But if I wanted to do VDU, then I would just write it the other way. But since I'm multiplying, it doesn't really matter. Okay, so multiplication and adding, the order doesn't matter, but when we get to like subtraction and division, then we need to be more careful. All right, any other questions right now about either example 7 or example 6? All right. So if there are no questions on that right now, we're going to stop this video here.